Welcome to Decoding Healthcare Research, a podcast by Agora Project. Join us as we delve into the behind-the-scenes world of groundbreaking research and the dynamic healthcare industry, interviewing top paper authors, engaging experts on industry-related topics, and exploring medical subjects that affect our daily lives. And now, your host, Dr. E.F. Rain.
Welcome to Decoding Healthcare Research. I'm your host, Efrain Riveros, Dr. E.F. Rain. Today, we will continue exploring the different aspects of obesity, specifically the role of insulin sensitivity, this time in the central nervous system. To discuss this particular topic, we invited a very special guest, Dr. Stephanie Kullmann. She's the Deputy Head of Metabolic Neuroimaging at the Institute for Diabetes Research and Metabolic Diseases at the University of Tübingen in Germany. Welcome, Dr. Kullmann.
Thank you so much for having me.
As we started developing this topic in depth, we have focused mainly on the peripheral aspects related to metabolism and the action of insulin. But I see that that you have been focusing more on the effect of insulin on the central nervous system. So I guess my first question to you is exactly that. What was the reason why you have this interest in insulin in the brain? What is the motivation? And tell us a little bit about your research.
Yeah, so I come from the exact opposite side. So I studied neuroscience. So for me, the brain was always at the center. And I've noticed really quickly that, each community sort of has its main focus. I was only focused on the brain, but then really realized there's this strong communication between brain and periphery. And I was really interested to see how that sort of shapes the decisions we make with respect to why do we decide what we eat. And I was always curious about how, the peripheral organs communicate with the brain about our current state. Do we have enough nutrients? Are our glucose levels high enough? So I was really always interested in this interaction brain-body. So that sort of, I think from the very get-go, sparked my interest from the neuroscience perspective. And yeah, since diabetes and obesity is such a huge problem, not just in the US, but across the world, I think, there's a lot of research now going on to that direction.
You mentioned brain sensitivity to insulin. What do you mean by that? Can you elaborate a little bit more about this concept?
Yeah, so that's a really relevant question because, of course, from the basics we know, the brain does not need insulin to take up glucose. It's independent of that. So it's been sort of neglected, right, with this whole research of obesity and diabetes. But it has a quite specific role that is very different from the rest of the body. It's very important for regulating how our appetite control. So if insulin does its job right in the brain, if it does it in a correct way, then after we eat something, we should feel satisfied and full. It should give our brain a sort of feedback mechanism of it's been enough, I'm satisfied, and I can go now on to something else. So a sensitive brain region to insulin, and that's still very strong up to research. So all the mechanisms are not known, but there are two aspects. One is our receptors in the brain. So we have insulin receptors in the brain, which made a lot of researchers curious. If we don't need it for glucose uptake, why do we have so many insulin receptors? And we see that these insulin receptors are not as sensitive anymore to insulin. And there's this hypothesis, which has also been shown, that there's a sort of a transport from of insulin getting into the brain that is sort of disturbed. These are the two aspects, what probably it means, insulin sensitivity and brain.
I was impressed by the methodology of the study. You used very sophisticated methods. Can you tell us a little bit more about how you conducted the study?
Yeah, so since I'm really interested in free living people, how a person who's very strongly fighting the battle of trying to lose calories, trying to lose weight, trying to really go on a diet and stick with it, we investigate participants who are either overweight or obese, and then we want to do this, of course, in a non-invasive way. So we use different kind of imaging techniques. That's at the center of how we measure the brain activity to insulin. And then we also think about, of course, what is the physiological setting? That would be, after eating a meal, our insulin levels go are elevated in our body, and we could measure the brain response to that. And we did this for a while. But then, of course, we noticed that we have now a mixture of all kinds of signals. All kinds of other gut hormones are activated by eating a meal, not just insulin. And then we have all kinds of peripheral signaling. So we really wanted to just look at selectively how insulin acts in the brain. And that's why we sort of used a method also used by other researchers called the intranasal insulin approach. So insulin is in a nasal spray, and we use this as you would use a normal nasal spray when you have a cold. You apply this, and it reaches the brain through what we call the olfactory pathway. So through the epithelia, olfactory epithelia, it gets into the brain. And we know from different research that around 30 minutes we have our peak activation pattern. And this has been shown also in animal research and from colleagues in rodent models. And we apply this basically in our human research.
So when you administer insulin intranasally, do you expect to see any systemic effects, or that insulin goes straight to the central nervous system?
Yeah. So on the one hand, that's a very relevant question. On the one hand, it does go directly to the brain, but of course, there is a slight spillover also into the periphery. We've been able to measure this. We do see that our glucose levels stay quite stable, but there's a slight spillover of insulin. So we were interested if there's any systemic effect, in a sense of that if once the brain is activated by this insulin stimulus through the nasal spray, do we now see systemic effects? That was actually a question that me and my colleagues were asking. And that's when we basically use we double designed. We use this intranasal insulin approach, but we use another approach used for peripheral measurements, and that is usually the hyperinsulinic euglycemic clamp technique. So it's a technique to measure whole body or peripheral insulin sensitivity. And there we've actually been able to see that indeed, if the brain is sensitive to insulin, and what we can see with this nasal spray approach, we see with these gold standards for peripheral measurements that actually directly associates or directly activates pathways in the periphery to enhance insulin sensitivity, but also to enhance insulin secretion and also hepatic processes.
I saw that in your paper you established very clearly the effect of exercise, and you separate it from the effect of insulin. So let's talk about that effect of exercise in the context of the administration of insulin. How does exercise affect the insulin sensitivity of the central nervous system?
So exercise, of course, it's very health promoting. So we have an increase in blood flow in the brain, and overall also what has been reported, an increased beneficial effect on cognition. And we were now really trying to pinpoint, but what is with the effect on insulin sensitivity in the brain? So by using this design, as I just mentioned, with the intranasal insulin and the brain imaging technique, fMRI, we then investigated participants before and after 8 weeks trial, where they basically were obese and overweight and haven't had a lot of experience with exercise. And what we see is, on the one hand side, is that these individuals, even though they're very tightly controlled, they really don't lose a lot of weight. But when we take a closer look at their brain function, what we do see is that specific brain regions are quite sensitive to exercise-related changes, specifically with respect to the insulin stimulus. And that is a part of the so-called dopaminergic circuitry. So regions in the brain that are dependent on dopamine, so regions in the striatum, they seem to be very little responsive in these individuals prior to the intervention. But once they've exercised for multiple weeks, we see that these striatal regions become more and more sensitive again to the insulin stimulus, which is probably also, from the mechanistic point of view, linked to dopamine function. But we see that this region now becomes responsive again, similar to what a healthy, normal weight a person would be. That is really also strongly linked that to the amount of visceral adipose tissue, this unhealthy belly fat that they lose. So on a scale settings, if they are on a scale, their weight is still quite the same. Maybe they lost a little bit, but not much. But actually, their belly fat that we also measure with MRI is already reducing. So for me, again, this interesting link again between brain function and periphery.
So you saw those changes in the hippocampus and also in the striatum. So how do you correlate those changes to the behavioral component. As we all know, the appetite and the behavior that is driven by those changes in appetite have to do with the metabolic components of this cascade. So what is the correlation exactly?
Yes. So of course, I mean, these are all correlative approaches, and we need definite, for example, animal models to really go into this mechanistic findings. So what we try to do is that we, on one single measurement day, we have multiple measurements. We have different cognitive measurements, so cognitive testings, we have functional MRI and whole body MRI, so that we sort of get this full picture of the responsiveness. But these are naturally, those are still associations and need to be shown that there's a causal link. But based on that study design, what is really intriguing is that the motivation might have been different between these individuals, yes, but we basically controlled it that all their exercise sessions, everything that they did, was next to a sports medicine physician, meaning we know exactly how much they exercised, how many minutes, and under what. It was a very controlled setting. And it was still very interesting to see that some individuals, they're very responsive. Also, their skeletal muscle was quite responsive to exercise, so meaning they improved in fitness quite strongly. And others were not as responsive, even though they showed the same motivation in a sense. They performed the exact same procedures as everyone else. And we believe from our findings that one key element is actually how sensitive they already were at baseline to insulin in the brain, and that those individuals who are quite insulin resistant actually struggle more to have a beneficial effect.
What type of exercise did you use for your protocol?
So that was a classical endurance exercise training, so aerobic exercise, so basically walking and cycling. And currently, we're now really wanting to know if that's really specific to aerobic exercise. So we're doing also further research on that, if that's specific to this. But that was endurance training, aerobic
Do
exercise.
you anticipate that resistance training and isometric training may also have a significant effect?
Yes, so I mean, honestly, we don't know, but I think it could also have beneficial effects, since it's known that also resistance training improves insulin sensitivity, or I would say peripheral metabolism. How that is linked to the brain is currently not known.
What do you think is the significance of your findings, and how do your findings build on what is already published in the literature? Patients and for the whole understanding of the pathophysiology of insulin and its different actions.
Yeah. So it definitely adds to the fact that this whole concept of response and non-response, so that this whole concept of individualized or personalized medicine, that we have individuals who might benefit from another type of therapy because they are brain insulin resistant. And we have to figure out also what regions in the brain are insulin resistant in these individuals. In this exercise study, we see that the hippocampus and striatal region is adaptive, or can change or improve its sensitivity with some also benefit. But we also know that other regions more is related to homeostasis. The hypothalamus can become insulin resistant, and their exercise might not necessarily be the exact right method to improve insulin sensitivity to the brain. There might be other pharmacological interventions, for example. So I think it adds to the fact that I think brain insulin resistance could be a key element in finding out why some people are just not responsive to the treatments that we have currently.
This is definitely opening new windows for other researchers to continue exploring these important aspects that you just mentioned. So for your particular group, what is coming next? What is the next step in the research that you are doing to try to elucidate the mechanisms involved in the insulin sensitivity in the brain and other aspects related to metabolic syndrome and metabolism in general?
One large aspect that is still missing, and I think we already talked about this in the beginning, is that, of course, each researcher has sort of a focus based on their individual scientific background. But now in the community, we've been really joining together, seeing that in Alzheimer's research, they also see there's a type of brain insulin resistance related also to cognitive dysfunction, even in persons who are in the periphery insulin sensitive. So sort of opening this whole concept that peripheral and and brain insulin resistance can correlate in some settings, some individuals, but not necessarily to all. So there's a sort of aging-dependent insulin resistance that is not well explored currently. So that's one, I think, very important aspect, because brain insulin resistance is also sort of linked to poor cognition. And another very important aspect that I'm now currently pursuing is also this differences between men and women. We also see that males and females respond quite differently in certain brain regions to insulin. And we've been figuring out that certain sex hormones really contribute to this. So that is another line of research that's really interesting to us, to see if there are any sex-specific findings.
For a lay person, besides exercise, what could be beneficial to try to restore insulin sensitivity in the brain?
So for those individuals who are already in a pre-diabetes state, so already very high risk to develop a diabetes, we've seen that also using pharmacological interventions like SGLT2 inhibitor actually improved the hypothalamus response to insulin. So certain medications or pharmaceutical interventions could help there. And there's also specific interventions looking into calorie restriction and, of course, regular dietary approaches. But there, of course, we have, again, this issue with a lot of our designs, is that we can help these individuals on a short-term setting, but then over a long run, they regain weight. So it has been shown that insulin sensitivity also in the brain can be improved on a short-term basis with weight loss, independent of the method you use. But currently, we're still lacking this approach of how can this then translate into a long-term weight maintenance success for these individuals. I think that's a line of research that's really strongly being pursued. And I think also with these now new medications that came out really with the GLP-1 agonists, really going to that direction that also targets very strongly the appetite center of the brain. I think there's a lot of work still to be done there, how that can be facilitated.
So the way you summarize all your findings is very organized and give us a good idea about the findings and how the brain sensitivity to insulin is definitely a factor that we need to factor in when we talk about metabolic syndrome, diabetes, and all these metabolic consequences. So I want to wrap up this conversation by thanking you, and again, thank you for the honor of having you here, for sharing your knowledge with us. And for our audience, you will find the link to the paper that we discussed today in the description of the video. See you in the next episode.
Thank you so much for having me.
Thank you so much for tuning into this episode. If you enjoyed it, please don't forget to give us a thumbs up and share it with your friends and family. Make sure to subscribe to our channel and hit that notification bell so you never miss an episode. If you have any questions or thoughts about today's topic, we'd love to hear from you. Feel free to leave your comments down below. For more information and references related to today's discussion, you can find them in the video description below. We appreciate your support and look forward to having you back for our next episode.